Okay, we will start. So today we'll give a review of the proofs. So the first one is the direct proof. Let's see a few examples. The first one we had for this direct proof is about the vertical angles. Vertical angles, you have intersection of two lines. The angles share the same vertex right across each other. We call them vertical angles, a pair of and beta. Okay. A very simple theorem. So here, two angles that congruent is they have the same measurement. We give a proof of this theorem, and that proof is a direct proof. We'll consider this angle, gamma. The observation is alpha and gamma, they are supplementary angles. And beta and gamma, they supplement angles for this line. This implies the two vertical angles must be the same. They have the same measurements. Implies this is a direct proof. Okay. We have more examples of direct proof. Another simple fact. If n is an even number, then n squared is also an even number. So we will prove it using the direct proof. Give me a check. Aaron, how would you prove this theorem?
Let's see. I do a contraposition by saying that if n isn't even, then n squared isn't even.
Okay, if we will go to the contraposition later, when we see the contraposition, we have to reverse the orders of the propositions. Okay, we'll see more about it later. So here we use a direct proof. N is even. It means n is 2k for some integer k. Then n squared again, this is an even number. Again, so this is a direct proof. Okay. Now let's consider another one. When we use this fact, it is a very simple fact. Let's use it to prove the following proposition. Okay, let's see how we prove this. We're going to show that if x squared is bigger than y squared, then x must be bigger than y. So to prove this, we will rewrite our assumption. X squared bigger than this, so the difference is positive. Okay. Kira, did the formula for the difference of two squares, do you remember that formula? Uh-huh.
X squared minus y squared. Hang on.
Equals to,
X squared minus, wait. X squared minus y squared equals,
it would be the product of something.
I think I'm forgetting. I remember like, x plus y times x minus y. Yeah.
Yes, nice. Yes. So the product of x plus y, x minus y. So we know this is positive. Okay. Now let's see what we have now. But this product with the condition is x plus y is positive. So we know this is positive. Then by the previous fact, this implies this factor, the second factor is also positive. Then we add y to both sides. Okay, so this is another direct proof. So you can see this direct proofs. It starts from what we know or what is given, then try to derive what we want. The second method of proof is proof by contraposition. Okay, some books they also say proof by contrapositive. So essentially the same. So what is a contraposition? It's the construction of a proposition. So in logic, we use lowercase p for a statement. A statement, what is a statement? It means it's a statement that's either true or false. Like the examples we had before. It's raining outside? It's sunny outside? The road is wet? The road is not wet? So this statement has a value true or false. We can tell it true or false. Some statements, they are conditional. If P and Q. Because there's a proposition. A proposition can be true, can be false. Okay. Let's see. One, that's two. Jessica, here I give you a statement. Can you tell me it's true or false, this statement?
True.
This is true, but I can give a different one. Give me a different one. Amy, can you hear us, Amy?
Yeah.
Okay, let's turn on the camera if you can.
Oh, I kind of forgot about that.
Okay. Now have a second statement. This statement is true or false.
False.
So this statement, it has a value true or false. This one we know is true. This is false. Okay. Some propositions may be also true or false. Let's see some examples. Okay, let's consider this one. If 1 is bigger than 2, then I is a real number. If we consider them individually, 1 bigger than 2, we know this is false. I is a real number, again, this is false. However, this proposition is a true proposition. This if condition is false, so this is never checked. But because the assumption is never satisfied, so we never check whether this is true or not. A true proposition kind of but useless. Because the condition is false. Some proposition, now we go to the construction of the contraposition. So that we will introduce the negation. We use the following symbol. We put a bar with a turn, not P. So we read this as the negation of P or not P. For example, if I say the negation, so P 1 less than 2, what's the negation of P? Fred, can you hear me, Fred? Okay, let's turn on camera, Fred. Okay, so the negation, not P. So now we have a statement, 1 less than 2. What's the negation of this statement? So 1 is not less than 2. Okay. 1 is not less than 2. Because we know they are both real numbers, we can compare them. So this is the same as 1 bigger than or equal to 2. So this is the negation of the proposition. Of course, we have learned algebra. We know this one is a true proposition, true statement. This is a false statement. Another statement, Q. Sophie, can you hear us, Sophie? Okay, Kira, if this is the statement, what's the negation of this statement?
I is not a real number.
Yes, so I is not. Then the contraposition. negation. Negation. Be careful. So we switch the order. P to the negation of P, Q, negation of Q, we switch the order. There are several statements. If we construct this Q minus imply P, this is called the converse. Negation P, negation Q, the inverse. So now we have a proposition and the three derived propositions: the contraposition, the converse, and inverse. We will focus on this one at the moment. In the future, you will learn more about this too. You notice that there's very subtle differences between converse, inverse. So this will come later. Okay, a simple practice.
Excuse me.
Yes.
How about the Venn diagram?
Okay, we will come to it. We will come to it. Okay, well, so the order is a little bit different from there.
Oh, okay.
Okay. Mhm. So this is a very simple fact. We all know it is true. Now we want to justify that. How do we prove it? What do we expect from a mathematical proof? Proof by contraposition. Let's consider a statement. What's the negation of Q? Aaron, for this statement, what's the negation?
Let's see. Either y equals 0. I mean, y is not 0 or x is not 0. Either that or that.
Okay, either. So that's a first response.
Or I could say or.
Is this what you want?
No, y first and then x second.
Or you want to go this? Aaron?
Yeah.
Okay. So now let's go to the Venn diagram. follow your order. Okay. This time we can see these two statements, they are not complement to each other. They're intersections between them. Okay, let's see what's the intersection. For example, let me check. X is 0, Y is 1. Aaron, does this satisfy this statement? Aaron,
Yeah.
does this satisfy the negation?
Well, I guess, yeah, because Y is not 1.
Okay, so now we can say if this is the negation, we would have a case that make both true. This cannot happen if this is the negation. A statement and its negation can only have one truth. You cannot be Q and not Q, right? So here we have to modify the statement. Okay, let's think about it. How do we modify this? What's the negation of the statement? Now I'm going to draw a picture. Oh, maybe the axis is, let's use the coordinate system. Easier to go this way. Okay, so our proposition is either x is 0 or y is 0. So this is true on the two coordinate axes. So the negation will be the complement with the rest of the coordinate axis. So in the rest, we can say here x not 0, y not 0, x not 0, y not 0, x not 0, y not 0. So the negation and both has to be true. This is the complement. Aaron, does it make sense?
Yeah, I felt it.
So, okay. So now this is a negation. If the statement is or, the negation will be and. Okay, let's have some practice. Let's find a few contrapositions. Okay, so this is the hypothesis. If n squared is even, then n is even. Amy, how do you construct the contraposition of this proposition?
If n is not even,
Mm-hmm.
then n squared is not even.
Okay, very nice. Exactly what the contraposition says. The negation of Q implies the negation of P. Under the hypothesis, it's an integer, so this is the same as okay. So to prove this proposition, it's not easy to prove this directly, but we can prove the contraposition. The contraposition is we can give a direct proof of the contraposition. Then this implies the initial proposition. So we prove this because if n is odd, if it's an even number plus 1, then n squared. So n squared is a summation of even number with 1. N squared is also odd. The direct proof of the contraposition give a proof of the initial proposition. So we call this proof by contraposition. Okay, so these are the steps to give a proof by contraposition of the proposition. So first, we construct the contraposition. Then we give a direct proof of this contraposition. This can be viewed as a proof by contraposition. Okay. Another one, so they're not easy to prove in the direct approach, but it's not difficult if you have the contraposition. Okay, let me pause for a few seconds. Any questions about this one?
Where the 2k plus 1 come from is my question.
Okay, so what do we say about an odd number?
Well, I do see a plus 1, and that makes sense, but what about the 2k? Couldn't.
So an odd number is an even number plus 1.
Oh, so the 2k is even, I see.
Right. Otherwise, if this is odd, the summation, if we add 1 to an odd number, we get an even number. right?
Oh. I would have written it as 2x.
Okay, you want 2x.
Yeah, if
Okay,
possible.
okay. So some of you prefer 2x. Some here, why do I pick k instead of x? Because normally x is stand for a unknown number. It could be a fraction, could be a decimal, right?
So
If
k is
we
an odd number.
so if we use k, normally we say k is an integer.
Oh,
So the letters, for example, we use n, k, this for m, p, q, all for integers.
okay, I see.
If we use x, y, z, it's for more general numbers.
Okay.
Okay.
That makes sense.
Okay. Other questions? Kira.
I got this part, but for the I didn't really understand like the previous part
Yeah.
because it was
So,
like
you mean here?
no, like under sort of.
So here.
Yeah.
Okay, what does this mean? Okay. Let me redraw this. Let's consider a simpler case. Let's redraw. It's different from previous one. Set. Okay. We use this for a collection of elements. A set. Now, if we consider a different one inside, so every element in B is also an element of A. We call B a subset of A. There are other cases, the two sets, they are not subsets to each other. A different situation. It's not a subset, but we can consider the intersection. We use the notation for this. A, the intersection. For example, A consists of the real numbers, and the B consists of the real numbers. Now let's see what's the intersection. Kira, do you want to try this one?
So that would be all the numbers greater than 1 and less than 4 at the same time. So that would be like
Okay. Mm-hmm.
yeah.
Yes, yes. Okay, so this is the intersection. It satisfies both conditions, bigger than 1 and less than 4. This is called the intersection. Okay. Now if I change A x greater than 4, B x smaller than 1, what's the intersection?
That's not possible.
Okay, so in this case, we say the intersection is an empty set. They do not intersect. We use a symbol. It's kind of a variation of 0. With 0, put a cross over there, indicate an empty set. A set contains no element, means they do not intersect. We also use the complement. We have a bigger set. We call this X. In this bigger set, I have a smaller set. I call it A. Then the complement. Is what's left, what's outside of A. So the complement, we pick this C to indicate the complement. I put C on the shoulder, indicate it's the complement of A. Okay, now the contraposition. How do we draw the diagram to indicate the contraposition? Okay, so A is a subset of B. Now let's compare the complements. The complement of A, it will be everything complement of A. And the complement of B. Okay. Jessica, what do you say about the two complements? A is a subset of B. Are there the connection between the two?
What was your question? I couldn't hear.
Okay. Are there connections between the two complement sets? Is one
Yeah.
bigger than the other?
What?
We have subset, or this is subset, which is a subset of which?
I don't know.
So the complement of A will be all the rest of A. Complement of B, the rest of B.
Oh. So A is complementing B.
So here we can see the complement of A is this. Complement of B is only part of this complement.
Then it's the other way around.
Yes, it will be the other way. Now we can rewrite this as A is a subset of B is equivalent to complement of B, complement of A. This is exactly the logic behind the contraposition. So P imply Q. Negation of Q imply negation of P. The connection between the logic and the Venn diagram. Aaron, this is what we are talking about, the Venn diagram.
I see.
So here, P to Q negation of Q, negation of P. Why
Looks
we
It looks
Yes.
just like that one on the top of that.
So why do we change the order? Because if we consider a smaller subset, the complement is bigger. So A, the subset of B, same as complement of B, the subset of the complement of A. So the complement in this case is the rule of negation.
Wait, is it something as the complement of X? Is there such a possible thing?
So here I put this X over there. This is the very important but often omitted hypothesis. Let's see what this means. If X is all real numbers and A is the numbers X bigger than or equal to 0. Okay. Now what's the complement? Amy. This is the whole space. This is a subset. What's the complement of the subset?
I'm not really sure.
So let's draw a graph here. The real line, all real numbers. So our set A will be all of this. So what's the complement, Amy?
Like the other side.
Yes. Okay, so if we have this, now we can see the complement will be X less than 0. Okay, let me change the condition. All complex numbers, I have the same set, A, X bigger than 0. What's the complement? Jessica, could you show this on the graph? So this is the complex plane. So this is set A. How do you draw this set A? This time, A consists the same thing. It's this ray over there. Let me use a different color to emphasize. So this is our A. It's too thick. And this is good enough. Now on the graph, we can see the complement of A is much larger. Not only this, but the whole complement. Complement is much larger. So whenever we talk about the complement of some sets, we should have a default ambient set. What's the bigger set we're talking about? Are we talking about the real numbers? In this case, this is the complement. We talk about complex numbers, then this will be the complement. So the complement depends on the whole set Amy, does it make sense to you? What do you think? So
I don't
the
know.
complement, so we have the same notation, the complement, but when the big set changes, same set with different complements. Okay, so why do I emphasize this? This is related to our construction of the negation. For example, the negation Pi is a real number. Under some conditions, we see the negation. So this is questionable because normally if we use this proposition, we would be talking about the complex numbers. The complement of real numbers over there is not just imaginary. It's the whole complement of this. Similarly, Q. The complement of Q. Some may say I square less than 0. The issue is when we talk about complex numbers, the square may be not real. If it's not a real number, we cannot say it's less than 0 or bigger than 0. So this only holds on in general, we should say the complement, the negation is not. Okay, so this is about the negation and the contraposition. Let's have a 4 minutes break and be back at 8:30. Okay, let's have one more example of this proof by contraposition. That is not easy to give a direct proof. Again, it's very important to specify what the whole set is. So let X be a positive number. Okay, if X is an irrational number, then the square root of X because we assume this is positive, this is well defined, it's also irrational. If we want to give a direct proof, this is irrational. How do we use this information? How do we verify this? Not easy to go either one of them. However, the contraposition is much more easy to deal with. The contraposition. So, okay. Amy, this one, what will be the contraposition?
If square root of x is rational, then it's rational.
Very nice. Initially, we have no way to start the proof of the statement. But if we write down the contraposition, they are equivalent, but this one is much more easy to start. Then we'll see this is rational. Okay, Jessica, what does it mean when we say a number is rational? Jessica, how would you use this information? Kira, are you back, Kira? Okay, Fred, how would you use this information? Some number is rational. So a rational number we write as the quotient of two integers. So we can write this as P and Q are integers. With this, what do we say about X? Aaron.
X equals P squared over P squared over Q squared.
Okay, so this implies now we can see this number is the quotient of two integers. So by the very definition, it means X is a rational number.
And therefore XQ squared is equal to P squared.
No, therefore X is rational.
Oh, okay.
That's all we need.
I was trying to interpret that equation.
Okay. Yes, no, okay. We could, but it's not what we need. Remember our target is
Oh,
this.
yeah. X is rational, yes.
Yes, this is our target. This is enough for our purpose. So we write down X is rational. And so we can compare the initial proposition with its contraposition. We can see the contraposition in this case is much easy, much accessible. Okay, so in some cases, it's easy to go with the contraposition. In some case, we have the third argument, proof by contradiction. Okay, so what's the difference between proof by contraposition and proof by contradiction?
Contradiction is when something is wrong, while contraposition is like The opposite of that.
Okay, so the contraposition has a clear target, what we are shooting for. So the contraposition is very clear. It's the contraposition of the initial proposition, what we are shooting for. For this one, we're shooting for x being rational. But the contradiction is more flexible. We don't know what we are shooting for. During the argument, we arrive at a contradiction. The contradiction may be the first step, maybe the second step, maybe the combination of the two. At any moment, we have a contradiction between this one and the previous one. We conclude the proof. So this one has a clear target where we are going to, but this one we will check way back. The very typical example, and we have gone over it several times, is this proposition. Okay, so when we say proof by contradiction, we say we are supposed on the contrary. Okay, so this is not a contraposition because this is just the opposite of the statement. It's not the contraposition. Like the previous one, this is the contraposition of the statement. But this is not a contraposition. It's just the negation of the conclusion. So it's not rational, it must be rational. Not irrational, it's rational. So we have the hypothesis as a definition of a rational function. Okay. This time we made the extra assumption that it's simplified. The P and the Q are co-prime. Oh, it's the same as the greatest common divisor is 1. Initially, we may say, why do we make this extra assumption? Later, we will say, this is where we're shooting at the contradiction. How do we get the contradiction? We not with this, but with it's being simplified. This is where the contradiction happens. Okay. In our homework, okay, so I will skip the whole proof. Yes, Aaron.
Isn't it, so you're saying GCD times PQ equals 1? Or is that something else?
The greatest common divisor of these two integers is 1.
Okay, I
Right?
see.
So this is the comma, not the product.
I see.
Okay.
I thought that was the times.
Okay, yeah, a little bit misleading. Let me try to make it better.
Yeah.
Okay. Similarly, when we say square root of 3 is irrational. Again, we go to the proof by contradiction. Again, we assume it's simplified. Okay. The point of this is can be done and will be done after that it's simplified. Then later we will derive a contradiction with this. So we get the proof by contradiction. In our homework, we have this one. Square root of 6 is irrational. Okay. I mentioned that we have 2 proofs. What does that mean? What does that mean? So again, we prove by contradiction. Let's suppose it's rational. Simplified. Okay, so here I have 2 different approaches. We can go with the first one. So P is even. Okay, so the first proof, we use only the even factor. So P squared even, P must be even. P equals 2K, we plug in, we get that 3Q squared is also even. 3Q squared being even, 3 is odd. So Q squared must be even. Then Q must be even. P and Q both even contradict this fact. Okay, that's the first proof. Second proof. Second proof is the, so this side is divisible by 3. So this is also divisible by 3. So divisible by P. Okay, so this means divisible. Okay, so 6Q squared, P squared, 3Q squared. 2Q squared, 3Q squared. Again, it's divisible by 3. So this being equal is also divisible by 3. Now, P is a multiple of 3. Q is a multiple of 3. It contradicts the assumption is simplified. So 2 different proofs. The first proof is similar to what we have for the square root of 2. Second proof, similar to what we have for the square root of 3. Okay, so the last one we will introduce is mathematical induction. Mathematical induction, so it consists of 2 steps. Okay, we will start with a very simple example. So for this one, it's 2 to the power of n is bigger than n for all integers. Why do we need induction? Because this consists of infinitely many statements. For n equals 1, n equals 2, n equals 3, we can check them one by one, but we cannot check them infinitely many times. We can check the first 100, first 1,000, but there are a billion left. How do we check all of them? We need this mathematical induction to check all of them. A very simple one, let's see how the proof works. The base case will be the starting one for all n bigger than or equal to 1. So for this one, the base case will be n equals 1. N equals 1, 2 to the 1 equals 2. It's bigger than 1. Okay, very easy. Then the inductive hypothesis. We assume this is true for n equals k. Then we use it to prove the next step. So if we assume this is true, and we can derive the next one based on the previous one, then the next one on the previous one, next one on the previous one. In this way, the whole statement is proved by induction. Okay, so how do we prove this? We have this 2 to the k. Okay, so now we are going to use this hypothesis. 2 to the k is bigger than k. Okay. So this step is in which is the hypothesis. This way is bigger than k plus 1. In this way, we used the hypothesis to complete the inductive step. We establish the new fact based on the previous one. We can establish the next one based on this one, next one based on this one. In this way, we proved the case one by one.
A question.
But yes,
You said that in the proof that there's a 2 k to the k plus 1 powered, right? Then it says equals to k times 2. So what happened to that 1 is my curiosity.
What's that?
I'm just curious what happened to that 1 in the k plus 1.
You mean from here to here?
No, in forward on the proof thing. Yeah.
Which step? So how do we go from here to here? Or from here to here? So first step or second step?
First step.
First step. How do we go from here to here?
Yeah.
Okay, so how do we go from here? So we have the power rule. A to the x plus y. What's the formula, Aaron?
That's basically ax plus ay, I think.
Plus or time?
Oh, yeah, right, times ay.
So it'll be time. So here we applied this formula.
Oh,
2 to the k plus 1. 2 to
so
the
that's
k?
1 squared, I see.
No, just 2 to the 1.
I see.
So k plus 1, I split the power. I put the k over there, 1 over there.
I
Okay.
see.
Okay. Okay. So this step, the power rule. Next step, the hypothesis. So the remaining step, they're just the algebra. It's easy. So in this way, you establish the inductive step and let's complete the proof. We don't have to check them one by one. This inductive step does the work. Okay. Let's try a similar one. N factorial. Amy, have you seen it before, the factorial?
Yeah.
Okay, what's the definition of n factorial?
Oh, it's just like 1 times 2 times 3 times 4 up until n.
Okay, nice. So we will use this. I claim this is bigger than 2 to the n, but not for all n, for n bigger than equal to 4. Okay. Again, there are infinitely many statements. So we want, what's the base case? Okay. Fred, what would you say about the base case? Is the n equal to 1 or for different n? Okay, so this time the base case will be n equal to 4. Let's check if it is true or false. N equal to 4 was 4 factorial. Aaron?
4 times 1 times 2 times 3 times 4, etc.
1, 2, 3, 4. This will be 24. And 2 to the 4. It will be 2, 2, 2, 2, 16. Okay, for the base case, we verified this is bigger. Then the inductive hypothesis. N equals K bigger than 4. 2 to the K big. The inductive step. N equals the next one, K plus 1. We want to check this K plus 1 factorial. Is it bigger than 2K plus 1? Okay, so let's see what's this factorial. How do we go from K factorial to K plus 1 factorial? Amy, how do we go from K factorial to K plus 1 factorial?
You just like,
Add another one.
yeah.
We add K plus 1 at the end. So this will be K factorial with 1 additional K plus 1. Okay, then we use the hypothesis. Hypothesis, the K factorial bigger than 2 to the K. Now K plus 1. K plus 1 is bigger than 2 because K is bigger than 4. Bigger than 2. And this is 2 plus 1. K plus 1. In this way, we finish the inductive step. So for K, 4 to 5, 5 to 6, 6 to 7. In this way, we find the proof one by one. Okay, so we will stop here and we'll have some practice, some exercise on this proofs. Any questions?